Hello there, Mr. Clark here. Thank you for joining me on this video. The video is an introduction to energy, which is a physics or combined science topic for GCSE. These are the aims of the lesson. At different points in the lesson I'll be asking you to pause and to think about things and to try out some activities. So if you can be ready to do that. We are starting off with some key ideas about energy stores and pathways in systems. If you've met this idea before, then try and make a list of the energy stores that you can remember. So there are 8 energy stores: chemical store, e.g. In a fossil fuel, kinetic store in a moving object, gravitational store due to the position of an object in a gravitational field, elastic store in a stretched or compressed spring or rubber band, for example, thermal store in a warm object, magnetic store in 2 separated magnets that are attracting or repelling, electrostatic store in 2 separated electric charges that are attracting or repelling, and nuclear store released through radioactive decay, fusion or fission. These are the 8 energy stores. A key idea is that any energy can shift between stores. It does this by going along one of 4 pathways. These can be mechanical, electrical, heating or radiation. So the pathway is explaining the process of energy transfer. It's explaining how the energy transfers from one store to another. So we're now going to look at an example, a child coming down a slide. The starting point is going to be the child at the top of the slide, and our end point is going to be the child just sliding down just before they come off the end of the slide. So at the top of the slide, all of the energy is in a gravitational store. The child isn't yet moving. As she slides down, there's a shift of energy from gravitational store into kinetic store as she gains speed, and the explanation for this transfer is there is a force pulling the child down the slope. It's a component of the force of gravity, and we can label the pathway as a mechanical pathway. So we should also include in this the fact that there's some friction as the child comes down the slide, and that some of the energy will be transferred into a thermal store due to the heating effect of the friction. And we can represent that on the diagram as shown here, with a second line going from gravitational store, this time to thermal store of the environment. Right, so here is a question for you to think about. Consider a mobile phone charger, and that the charger is fully charged and it's connected to your mobile phone, and it's in the process of charging the mobile phone. See if you can identify the stores involved here and the pathway by which the energy is transferred between those stores. I'd suggest now you pause the video and have a think about that. So here we are. You can check to see if you had this correct. So energy starts in the chemical store of the charger and transfers to the chemical store of the phone battery, and it does this via an electrical pathway. There are electrical currents that are being pushed around by the charger. The charger is doing electrical work on the currents and pushing it through the circuit, through the phone battery, and that's the process by which energy is being transferred. So rather like we did with the child on the slide, we can now ask the question, have we accounted for all of the energy? So give that some thought and see if you can come up with some ideas. So we know that the charger will actually get slightly warm when it's in use. You may have noticed this yourself if you have a phone charger. And that's telling us that some energy is being transferred from the chemical store of the charger by heating, which is conduction or convection, and also by radiation, which is infrared radiation. Any warm objects will emit infrared radiation. Both of those are transferring into the thermal store of the environment. So ultimately, the air and the surroundings are getting slightly warmed up by the charger. The phone itself will also get warm, and there'll be some transfer of energy from the phone battery to the thermal store of the environment. Again, this is by heating and by radiation. So you can see here that some of the energy is transferred into the thermal store of the surroundings. We say that the energy has been dissipated, and this is a key term, and it's a key idea for you to learn for your exams. So let's say that you're watching a video on your phone, which you may very well be at the moment. We know that the phone is emitting light radiation from the screen, and it's emitting sound radiation from the microphone. So let's have a think then about the store where this energy comes from, and the store that then transfers to. So well done if you got this correct. So energy transfers from a chemical store in the phone battery to the thermal store of the environment, and it does this by the light rays and the sound radiation bouncing around, reflecting around off the surfaces and the walls in the room, and eventually all of it will be absorbed by the walls and the surfaces in the room, and there will be a transfer to the thermal store of the environment. So the walls and the surfaces in the room will get very slightly warmer. The next key idea we're going to look at is applying the idea of conservation of energy. So the law of conservation of energy is quite a simple idea. It just says that if you have 3,000 joules of energy to start with, you'll have 3,000 joules afterwards. So long as no energy enters or leaves the system, energy can shift around between stores, and in total you'll always have the same amount of energy that you had to start with. It can be helpful to think of energy as like money. If we start with £5 of money in our pocket and not spending it to start with, that represents energy just staying in one store and not shifting, and we wouldn't see any change or anything happening. So we know that we only see a change when energy shifts between stores. A bit like the money here, if we just keep the £5 in our pocket, we don't really see anything happening with that money. When we spend it, then we get something in return, and that represents energy shifting from one store to another. And in total, the same amount of energy is out there in our closed system, even when it's shifted between stores. And so you can see with the money, there's still £5 in total out there. It's just that we've now only got £2 left in our pocket, but the shop owners have got £3 of our money, so there's £5 still out there in total. So that's representing the total energy remaining constant within the closed system. So in our phone charger example, if we started with 5,000 joules of energy in the chemical store of the charger, and 3,000 joules of this energy transfers to the phone battery, how much energy is dissipated transferred to the thermal store of the surroundings. Pause and think about that for a moment. Of course, the answer is 2000 joules. If we start with 5000, 3000 joules goes into the chemical store of the battery, then the remainder, the 2000 joules, must go into the thermal store of the environment, and that would be what we referred to earlier as dissipated energy. Of course, it's not ideal to have energy going into the thermal store of the environment. It represents wasted energy, and it's an important aspect of the design of devices and components to reduce as far as possible the amount of energy that is wasted. So we're now looking at calculating work done and power. Mechanical work done. So work done is a measure of the energy transferred in a system. We can use the equation work done equals force times distance moved, and that's helpful because we can very often measure the force in newtons and the distance in meters, multiply the two together, and we get the work done in joules. It's telling us the energy transferred, and that makes it a very useful measurement. Example: how much work is done if you push a supermarket trolley with a force of 100 newtons around a distance of 20 meters around a shop? Have a go at that and write your answer with the correct unit. So of course the answer is 2000 joules, J for joules there, 100 newtons multiplied by 20 meters. So well done if you got that right. So in questions you may need to use the equation to calculate the work done, or the force if you're given the work done and the distance, or the distance moved if you're given the work done and the force. So I would now like you to pause the video and to have a go at some calculations for yourself using the equation work done equals force times distance. You are allowed to use a calculator. I would strongly suggest you write down your working really clearly and make sure your answer has the correct unit. So here are the answers to those questions. If you'd like to self-mark your work, and you can make any corrections that you need to. So for the first one, it's just force times distance, so it's 5 times 10 equals 50 joules. For the second one, similar method, but we just need to make sure we've converted the centimetres to metres. So 7.9 centimetres becomes 0.079 metres. That will give us our 55.3 joules. For the third one, 3 and 4, we are asked to work out distance. So we need to do work done divided by force. So for 3, it's 400 divided by 25 equals 16 meters. For question 4, you may note we've got kilojoules here. 1 kilo of something is 1,000 times the value, so it's 4.5 kJ is 4,500 joules. Divide by 3.9 newtons equals 1150 meters, and that would be equal to 1.15 kilometers. For question 5, 6 and 7, we are asked for the force. So force is work done divided by distance. So for this one, it's 56 divided by 0.25, which is 224 newtons. For question 6, it's 3.1 kilojoules, or 3,100 joules, divided by 9.12 newtons. So that's 340 meters, or 0.34 kilometers. And for the last one, Same method, so it's work done divided by force, but we've got 53 megajoules. Mega is million, so we could write 6 noughts here, 56 million, and we're dividing by 2.2 times 10 to the power of 4, which is 22,000 meters, and that gives us 2.4 times 10 to the 3 newtons as our answer. So power is the rate at which energy is transferred. Power is calculated from energy divided by time, and because work done is equivalent to, it measures the energy transferred, we can also write power equals work done divided by time. So power is measured in watts, where 1 watt is 1 joule of energy transfer every second. For example, a 20 watt light bulb transfers 20 joules of energy each second. A 1 kilowatt iron transfers 1000 joules of energy each second. Here's an activity for you to try. Follow the instructions and you'll be able to calculate your own power. You need a step, somewhere to step up and down. You need a stopwatch, it could be your phone. You need a ruler or a tape measure to measure the height of the step. So measure and record the height of the step in meters. Count how many steps you do in a certain time, so it could be 30 seconds, and record the number of steps that you do. And then you need to use our power equation to calculate your power. So we'll use the work done divided by time version of the equation. Work done equals force times distance. In this case, it's equal to weight times the height, the total height that we've climbed during the 30-second time period. So that's why we have, on the top line, we have weight times height of step times number of steps. We divide that by the time. You'll see that our weight needs to be in newtons. So for example, if you know your mass in kilograms, you can times that by 10 and it gives you your weight in newtons. If you're not sure, then you can just use 500 newtons as your weight. Remember that the height of the step needs to be in meters. So if you've measured in centimeters, that will need to be converted to meters. So to give you an example, the woman in the video did 7 steps in 10 seconds. The step was 12 centimeters high. Her mass was 65 kilograms. So putting all that together, her weight is 65 times 10, so 650 newtons. Her total height was the number of steps that she did, which was 7 multiplied by the height of one step, 0.12. That gives 0.84 meters. Multiply 650 by 0.84 and then divide by the time, which was 10 seconds. She got 54.6 watts. So probably round that to 55 watts on the basis that there's some uncertainty in the timing. On this slide you can compare the power value that you got with the value of the power rating of different appliances. So that brings us to the end of this video. You may want to spend some time now just going back and reviewing each of the topics that we've covered and watching again if you feel you need to. And I'd just like to say thank you for your participation, and I hope that's been useful, and I hope to see you again soon.